Welcome, Z80 enthusiasts. This video is a video made especially for programmers who have very little electronic knowledge, who wish to make a Z80 computer on a breadboard that does something more than just read switches, put on LED lights, and so forth. So in order to do that, it would be a good idea to start with the videos that are already on YouTube that show you how to hook up a Z80 all by itself to show you that it operates by grounding the data pins and hooking up LEDs to the address pins and watching the lights, and you can see that it's operating, and it takes you so far, but to go from there to A to B to make a full-blown system that does useful work, it takes a little bit of doing, but I have done it. This is my computer. I actually have 2 or 3 of them. This one actually hooks up to a terminal with a cable, and you can read and write from the terminal. It would be very good also to read a book such as The Programming the Z80 by Rodney Zacks, and this Z80 microprocessor book, if you can get that one. There's the author. It also doesn't hurt to pick up a copy of the Junkbox Arduino, and because this book actually shows you in the last chapter how to hook up a Z80 to the Arduino. It's actually an 18 mega, I think it's a 128, and you can see how the Z80 works, put it through its paces. What you need to make this project are, let's see, these parts. You need a good screwdriver set, some pliers, needle nose pliers that is, wire cutters, strippers. You need a magnifying glass, preferably with a light on it, a good multimeter, some wires, good quality wire here, some green wire. Possibly you could use these wires, these jumper cables, and you also need to print out for each chip you're using a data sheet, such as the one you're looking at here, shows you the pin layout, as well as a schematic that you will follow when you build the computer. This video is in several parts. This is the intro. I then provide a hardware overview, and I have 2 software segments. Part A will show you the code I used, and Part B will show you how to burn the code that you in the Z80 assembly language, machine language actually, onto the ROM chip. What follows next would be a list of parts that you require. Here is the parts list for this project. And here is the link to the schematic. Before I give a demonstration of my computer, I would like to say a few words about the power supply that you need. You could use either 9-volt batteries, or you could use a DC power supply unit. When I first started building this computer, I used 9-volt batteries, and to do that you need a voltage regulator circuit. You can see I created one here in a modular unit. It just consists of 3 parts. It has the voltage regulator, which has the heat sink on top of it. It has 1 electrolytic capacitor. I'm using 2.2 microfarads, and then it also has a non-electrolytic capacitor of 0.1 microfarads. You can see how to hook this up in other videos on YouTube. There are plenty of them around to show exactly how to make one. But I recommend you get one of these DC power supply units. All you have to do is you turn this knob, and you can get exactly the right amount of voltage that you need. And this knob on the right is a minor adjustment. You can get exactly 5 volts. then you don't worry about the batteries running low. In this case, you can see that I'm getting 4.361 or so, and that amount of volts is insufficient to operate this computer. You need at least, I would say, 4.7, probably 4.8 to run this computer well. Otherwise, you're going to run into trouble. And if you keep using these batteries, they will run low pretty quickly. Okay, that's all I have to say about that. Now we'll move on to the demo. Okay, it's time to show a demo of this computer so you can see exactly what it does. I have a terminal running on my Linux notebook. It is running a terminal program called GTK-term. It is set at 1200 baud, 8 data bits, no parity, 1 stop bit. I have a DC power supply hooked up, set at 5 volts and 110 milliamps. I have an oscilloscope hooked up, and you can see a nice square wave. Hopefully you can see it says 2 megahertz due to the full can metal oscillator you see below, which is a 2 megahertz chip. So now what we have to do is show you what it does. So you can see that it has a clear screen, nothing on the screen. I will focus on this slide switch right here, which is waiting to be switched on. I'm going to switch it to the right. And like magic, on the screen, we have the text that you can see. It's waiting for me to enter some text. I will enter the text slowly at first. I will show the lights. You can see the LEDs. If you can make it out, you can see from the left, the second and third one are on, and the low order one, all the way to the right, is on, which is 61 in hex. See, you can see different colors. I divided those 8 bits into 2 groups of 4, which are the nibbles, as they are known, and that is lowercase a. Nothing on the screen yet. I will enter the next character, a B, and you can see you have a different configuration. Now you have 62, which is, in fact, lowercase b. Last but not least, I went to the C. And now you can see the 63. So I'm just echoing what I'm typing on the LEDs, but I'm not displaying anything until I hit the Enter key right now. And now I echo what you typed, ABC, display end of line, and I loop back to the top of the program, and I ask for some more text. And you can type pretty quickly, up to 80 characters, and it will echo them all, and continue until you enter an X on the screen, lower or uppercase X is a lowercase x. Enter, and the message, "Have a nice day," appears. Program ends. Okay, in order to reset the machine, you go to the reset switch, slide it back to the left, and now it's resetting. It takes a few T-states to reset. At this megahertz, which is 2 megahertz, it only takes about 1 or 2 seconds, but I waited a little longer, so you can switch it back, and a new message appears after "Have a nice day," and you start all over again. Now, we also have, in addition to the LEDs hooked up, we have some switches. Now, you can have 8 switches here, as you can see. I just hooked up the first, actually number 8. You can hook up the other ones, doesn't matter. So right now it's in the up position. I'm going to attempt to switch it down without popping up these darn switches from the breadboard. I want to push down on it. I think that's good. Let's see. I'm going to type. Yep, it was good. Now the program is determined that the switch is now off, and instead of displaying or echoing the text you type in, it's displaying the message "unknown name." And now again we'll exit, and there you go. Now, if you don't have a power supply, you can use a 9-volt battery. I have one in this case here. You just need to create one of these voltage regulator circuits, or you can buy one of those things that do the same thing. And I will not explain that because many videos tell you how to do that. They also tell you how to create the timer using a 555 timer, create an astable multivibrator oscillator. I won't show you that either. I won't show you or tell you about all the pins in the Z80, what they do, what they are, because you can also see that in many places. I'm just trying to explain what I haven't seen on YouTube videos when I was trying to make this computer, so that maybe it would be a lot easier for you to make one. In any event, I think that covers it. Oh, there's one more thing. Since I have shown you the 2 megahertz clock, I will show you the other clock. So I have 2 slide switches to control that. In this corner, you can see the slide switches. I'm going to flip them. And now, that sine wave, that square wave is not the wave for this. Let's see if I can do that. If I can take this lead out from the full can, and if I can hook up to the pin 6. Let's see. Oh, there we go. Let's see if I can get that to show. It's a nice looking square wave. Let's see if I can get, there you go, 15.82 hertz, which is a lot slower than 20 megahertz. And at that frequency, you cannot communicate with the terminal, but you can see all the LEDs blink, flash, up on, up on. You can see the red one in the corner is the read signal. The green one next to it is the M1 pin. And let's see. Well, let me remove this out of the way. You can see pin 20 and 19 on this side. 20 is the IO request, and to the left of it is the memory request LED. So I also have one hooked up to the RAM chip and on the ROM chip. Now this computer has the Z80. Let's see, where is my little pointer? There's the Z80. I believe it's 20 megahertz one. It could be 6. I have several machines I made. Now let's see, this one here is the flash ROM chip. And this one here is the static RAM chip. In between here is the memory decoding circuit. And between the lights, the LEDs, and the switches, you have the transceiver and the latch I'll get into later. And in this section on the end of the board, you have the IO decoding circuit, which I will get into later. So stay tuned as I go into the hardware and try to explain how this all works. This is the hardware section on wiring a Z80. Now, I had sent a link to this web page, and if you go to that web page, and that link is on the parts screen, so I put that elsewhere. But if you scroll down to section 27, you'll see some text. Continue scrolling, you'll see the schematic, which I followed for the most part in this project. This is done by, and let's see, McLeod IdeaFix. Thank you, McLeod IdeaFix, for this, because this made this project a heck of a lot easier to complete. As he explains in his text right here, pretty much everything you need to know to build it. He does leave out a few minor details, such as the use of bypass capacitors, how to hook them up, and his reset switch seemed to be a little confusing to me anyway, but I have never looked at schematics like this before, and to me, when I first looked at it, it was kind of intimidating. So let's see if I can clarify it just a bit. Okay, here we have a blow up of the schematic. He has the CPU. He has the ROM chip, and he has the RAM chip. He also provides for output through an LCD and input through dip switches. He shows in the thick blue line at the bottom the data bus, which is not really one line. Actually, it's made up of the 8 data lines. And on the top, he has the address bus, which actually consists of the 16 address pin right there. A0 through A15, all those pins. Now, if you were to do this on a breadboard, you want to implement on a breadboard, and you would have 24 lines going across, you would run out of holes for sure. So my solution was to hook up the data pins to a central location and then take them from there to where they needed to go. The address pins, I did a similar thing, but not to all of them. Only the ones that I needed for the decoding circuits. Okay, now, if you were to take a Z80, and especially if you started with videos that showed you how to ground the data pins and put LEDs on the address pins and watch the address lights bump by one as it executes each no-op, you'll definitely have to remove those grounded data pins and hook them up to something. So now what you want to hook them up to is the memory. So you'd have to tell the Z80 which chip is it going to access, the ROM or the RAM. To do that, he has provided in the schematic a memory decoder circuit, which consists of 3 logic gates, an S04 inverter, and 2 OR gates. There are 32 ends. Okay, so now what he's using is A15, that address line, A15. And he's using that to determine, are we going to the ROM or are we going to enable the RAM? So what he does is he inverts the A15, sends it to 1. I'll get my pointer so we can follow this. Let's see, A15 inverted, coming down to this one, which eventually will go to enable the RAM chip, and on inverted, but just plain A15 into the OR gate, which will feed the ROM enabled pin, and the other input to both ORs gates is the M request, which is active low. So now if you follow these lines, it'll take you to, let's look at the ROM one first. Okay, right, this is the ROM. You can see at the bottom, of this diagram, you have a CE, an OE, and the voltage pin. So the CE is chip enable, the OE is read enable. Actually, not, he did say OE for output, but actually it's the read pin that gets hooked up to that one, and it's the overall ROM pin from the memory decoding circuit feeding the CE. Now you see the bar on top, in case you didn't know it, that the bar indicates that this pin is active low. If it doesn't have the bar, it'll be active high. I would like to mention that some data sheets put the bar on top, like this one does, OE, and this particular chip is a latch. And, I have to go fetch it. This transceiver has an output enable right there. Let's see, I can show this. I wrote the OE in because they didn't bother to put the bar on top. I also found out that you can actually indicate that with a dash before the symbols, like dash OE, but that's beside the point. Okay, now, moving on. Okay, once you hook up, let me get this back. Once you hook up I'll put this up here. Once you hook up the Z80 to the memory, then you would want to know, is it working? So to do that, you can't just take the LEDs you can't just use them and hook them directly to the data lines. You have to go through what's called a latch. And because the signals on there are not kept for long enough to see them. So if you're doing an I/O instruction, an I/O would be, I request pin would be low. You won't be doing memory. Memory request will be high. If you're doing, let's say, an out instruction, then the write signal, WR, will be low. The read will be high. But you still won't be able to see what you expect to see on the LEDs unless you go through a latch, which he's using right here, which is the 74HCT573N hooked up to his LCD display. And you can see that there are two sets of data pins, and one is hooked up on the left side to the Z80 data bus, and the other side on the right hooked up to the LCDs through resistors. And let's see, he's got them marked 330 ohms. The bottom of the IC4 chip in his diagram, you see the C and the OC. One of them would be to enable the chip, probably OC grounded, it's probably active low, and the other C is hooked up to the, let's see if you can follow that with my pointer. Where did my pointer go? Well, you can, let's see, move this thing around. It's actually hooked up to this inverter, which is the part of the I/O decoding circuit below I/O decoder. So C in this case, let's get back there. Right. C is the actual, it's actually enabled only when you're doing the write. And the OC is to enable that chip regardless of reading or writing. It would always be active, in other words, if you ground it. Now, the other direction, if you want to go to the switches, you need a transceiver, which is using a 74HCT245N, and it also has two sets of data pins, an A set and a B set. He calls it IC5 in the diagram. So now one difference between the transceiver and the latch is that the transceiver has a direction pin, so depending on if it's high or low, the data will either transfer from A set to the B set or vice versa. And actually the pin below is the one hooked up to the I/O decoding circuit. Okay, now the I/O decoding circuit is very similar to the memory decoding circuit. The difference is that instead of using A15, he chose in his design to use A0 to distinguish input from output. So one of them, the one on top here, goes right into the top OR gate here. The other one goes to an inverter first before the corresponding OR gate is reached. And then the one on the top uses a read after that to combine with the output of that OR. And the one below uses a write to combine with the output of that OR. And then he sends them to the latches and to the transceiver. So that's basically how he does it. Now the reset circuit, he has right, a power on reset circuit, seemed to be a little confusing to me as to how to hook it up in practice. So my solution is right here, and this works perfectly. I took pin 26, which is active low, from the Z80 CPU, hooked up to the middle pin of a slide switch, the leftmost pin hooked up to the ground, the rightmost pin hooked up to the power rail. And so in one setting, let's say the left two most pins are connected, then pin 26 will be low and active, and therefore the Z80 will be resetting until I switch back, and I just slide the switch to the right, and then the rightmost two pins will be connected. Therefore, this pin 26 will then go high, and the Z80 will start executing instructions. A word about the bypass capacitor. Many people have said that the bypass capacitor, which in this case is a 0.1 microfarad capacitor, needs to be hooked up as close to the IC as possible. But I didn't see anybody explaining exactly how. But obviously, after a while, I realized that this is how you would do it in this picture. So you would have the power is here, the ground is here, but the, I actually didn't put it in this diagram, but the capacitor here has to come right, it has to be hooked up to the pins right adjacent to the IC, right at the top. And then from there, you go to the ground and power, if that's clear. The ground pin, in this case, cannot be hooked up to any pin in the IC. So therefore, it has to be to the right of the chip and no other pins connected to it. The one hooked up to the power rail is connected to the topmost pin, the power pin on the IC. Okay, now a little tidbit that I know. If you're running at a slow clock, say 7 hertz or maybe 15 hertz, you can see the control lights will blink. You can tell when it's doing a read, write, I request, memory request, when instruction is starting with M1. And you can, if you have a clock, obviously hooked up to the pin 6, the clock. If you can actually check the voltage on that with a meter. You can check the voltage on the power, which is 11, pin 11. Where is that? Let's see. Yeah, down at the bottom, pin 11. You can check that out. But I would like to say that if you're running at 2 megahertz, then you will not see the lights flash because it's too fast. On the other hand, if you run at, say, 15 hertz, you won't be able to connect to the terminal, as far as I know. So that's why I'm using 2 megahertz to connect to the terminal. I will discuss how to connect to the terminal, how I augmented these decoding circuits in another segment of this video. Okay, that is it for now. And stay tuned, and we'll continue on to the software segment next. This is the software segment of this video, part 1, where I will show you the code that was used in the demo, and I will show you how it relates to the decoding circuits. Let's take a look at a typical instruction. Okay, let's look at load HL, prompt. On line 33, the assembler has generated the code 212201, so the offset is 2201. But since the Z80 is a little endian machine, the offset is actually 0122. Note that in that case, the high order bit is 0. Now, when the load HL, prompt instruction is executed, the Z80 will load the address pins with the address that we just seen, 0122. And since A0 is 0 in this case, according to our memory decoding circuits, that means that we will be accessing the ROM. Of course, this assumes that the Z80 has set the memory request pin to active, which it does, because when you're doing a load of a register or pair of registers, HL, that's what will happen. Now let's go down, and a little bit down we'll see a contrary example. Here is a load HL, STR at line 39. The assembler has generated the code 210180, which is offset 8001. So there, in this case, the high order bit is 1, not 0. In this case, we will be accessing RAM. How do we get the assembler to do that? I will show you. I will scroll to the very bottom. And there is the definition of the variable stir. Defined storage 80 characters on line 246. There you can see the code of 8001. And this is how I did it, with an org instruction. So we just org with the constant value of 8000 hex, and that causes the assembler to insert this offset when in the instruction when this variable is accessed. Okay, now let's go on to the I/O instructions, the in and the out. Okay. Here is a typical out instruction. Out, first operand is the port number, and the second operand is register A. If you use this format with a hard-coded port, as opposed to the port value in register C, you need to use register A as the second operand. As you can see, I am loading register A with a hex value of 55 and attempting to write that out to whatever device is hooked up to this port. So now that port being a 1, LED underscore port, is defined on top of this program. It has a value of 1. That means a 0 particular will be set to 1. And according to our circuits, which I showed you earlier, that means that we will be outputting to the latch, which is connected to the LEDs. So this value will show up on the LEDs as the 8 lights will show as off, on, off, on, off, on, off, on. Now, in order for this to work, obviously, the Z80, being that there's an out instruction, needs to set the write pin active and the idle request active. The memory request will be not active. Okay, now let's look at an in instruction. Now, conversely, on an in, the first operand now is switched around. Now it is register A. The second operand is the port. In this case, the switch underscore port has a value of 0, and the read pin is now active instead of the write pin. And IO request pin is still going to be active. So you take those 3 pins, and if you remember how the IO decoding circuit was set up, that means that we will be reading from the transceiver, which is hooked up to the dip switches. I actually hooked up the switch number 8. So I connected that to D0. So whatever's in D0, whatever you read, will be from the switch will be sent to the Z80 on D0. That is how the in and outs work for the latches and for the switches. Now, to do serial communication, I had to enhance the original design just a little bit. The original design had A0 and I request coming into the first OR gate, and the read signal was used. This is the input section. And I added the one that's surrounded by the dashed red line, so I decided to use A1 in addition to A0. And A1 is hooked up to a new OR gate as one input. The other input comes from the result that was used before to enable the transceiver. And now the output of the new OR gate feeds the transceiver and activates that. Now on the other side, on the right side, I used A1, inverted it, instead of using it on inverted. And I'm feeding another OR gate as one input, and the other input comes from where the output was before. And now the output inverted from the new OR gate will now feed the latch and activate that. In this way, A1 will be used to determine whether I send and receive data to and from the terminal, or do I send data to and from the latch and the switches. Okay, now how to do serial communication. When I first tried to do it, I have, as an example, an RC 2014, which I built. A very nice kit from England, from the Tindy company. And it actually works. It's pretty amazing. Nice kit. And I figured, why don't I use the same method of serial communication that this uses? Well, it uses a ACIA, Asynchronous Communication Interface Adapter IC. And, well, to make a long story short, it didn't quite work out for me. And then I was thinking of, maybe I should use a Zilog SIO chip. And I said, well, that's going to be more complicated to initialize than the other one. So then I went looking, and I found this book. And this is a great book because it tells you exactly how to do this in software. It says you can do it in hardware, which they show you, and then you can also do it in software. They actually are nice enough to show a nice flow chart for transmit and for receiving. So basically I follow the flow chart in my code right here. But to do it, you have to understand a few things. Let's see about serial communication. That is TTL, transistor-transistor logic serial communication. So it's actually, in concept, it's pretty simple. So here is a diagram I found showing you a start bit, the data itself for the character you're sending or receiving, and the end bit, which is the stop bit. So then they're showing you that you start high, then when you start, you're sending it a low signal, and then for each bit in the data, you send high or low, depending on what the data bit is, and then you send an end bit, which is high. But you also have to realize when you send data to the terminal, you need to send the low order bit first. And you also have to know that you have to keep the signal high for the line in question. If you don't keep it high, terminal won't know when you're starting. And then once you get this right and you code a routine to read and write a character, then you loop through that and you can read or write a string. Now, getting back to the code, what you need to do in this code is actually calculate a value that you need to use as a loop counter so that you can actually send the data at the right time. Because this communication is asynchronous, it doesn't use a clock, so the timing is critical. Now, to do that, I will find code. Let's see if I can find it. Here we go. Okay. I have a value delay underscore count 1 here, loading to register C. I have a very short loop, very small, only 2 instructions are in the loop, decrement C and jump.0 delay 2. So now, since it's very short, it only consists of 2 instructions, all you have to do is calculate how long each instruction takes, and then once you have that value, then you have to calculate how long all the instructions that are not in that loop, but that are needed to do the operation you require, such as converting the parallel to serial and vice versa. And you calculate that, subtract that from the value that you need according to the baud rate. And then, when you know that, you know how many times to iterate around that small fixed loop you have to give you what you need. So here is my example. I used 1200 baud on my terminal. I divide 1 second by 1200. I get this value, which is 833 microseconds. That is the time we need to delay between sending or receiving a single bit. Okay, now, to do that is not complicated because the Z80 is very easy to see how long each instruction takes. You can get a reference. You can look at a book like this, Rodney Zach's program, the Z80, and you look at, say, a load instruction, load RN, and you look below and you see the timing is 2 machine cycles, 7 T-states, 3.5 microseconds at 2 megahertz, which is why I use 2 megahertz, because a lot of references at the time use 2, and it's also very easy to calculate. In that case, you would just take the number of T-states in 7 divided by 2, and you'll have the time it takes to execute the instruction. In this case, 3.5 microseconds. So now you know how to calculate the time between sending bits. Just have to code it. Now, other thing to realize is that when you're sending data, and I will show you one of them. Let's see if I can find one. Okay. Oh, one more thing before I do that, before I forget. How to keep the line high in the beginning. That's important. Because when I first did this, it didn't work at all. Blank screen, nothing. Why? I was thinking a few days and it occurred to me, how do I keep it high? How does the terminal know I'm starting this process? Well, since you have to keep it high, I decided to load on line 196. I loaded register A with the value of 1. And then I put the loop counter as 100, an arbitrary value. And I didn't put a delay between sending anything out. I just looped around 100 times, sending it 1, 1, 1 to the output terminal port. And that kept it high, and it did work. Then I started sending the start bit, looping through, sending each bit of the character. And to do that, and then sending a stop bit. Now to do that, to actually send the data, since we know the data we're sending, the entire 8 bits, we know that we have to send the low order first. That's also important to know. You need to send the low order bit first, and you receive, you will be getting the low order bit first. Therefore, you have the whole value that we want in a register. So we will send the low order bit, and then we will shift the register that the data is in one bit to the right, and that's all you can shift with Z80 is one bit at a time anyway. And after 7 such shifts and sending, you'll have the whole byte sent. And for input, it's a little different. In input, you're getting the low order bit first from the terminal. So in that case, you would put it into D7, the higher order of those 8 bits, and then you would shift them over to the right one. And when you're done with 7 shifts, you'll have the whole entire value of the character typed in on the keyboard in that register you're loading. So now, with that said, you need to hook this up to the terminal somehow. To do that, you need some cable like this. This is what I used. It has a USB connector on one end, hooked up to your laptop, let's say, and it has a 6-pin connector, as you can see. Okay, so now you can see those header pins. Well, I have a Cestino I built. You can see the pins here. Yep, there they are. So how do you hook them up? Well, here's the diagram. You can look this up, but I'll just show you because it's pretty straightforward. These are the 6 pins. Request to send, receive, transmit, power, clear to send, ground. The RTS is not used at all. The RX and TX are used. I'll get to that in a minute. If you want power from the laptop, you can use pin 4 and the 5 volts or whatever will be on there. The CTS is hooked to ground. I think that's because you always want to enable whatever you're doing. And the ground obviously is hooked to ground. Now the RX and TX, getting to that. We're using D0 and D7. I just showed you about input and output, why you would use D0 and D7. But exactly how do you hook this up? Well, you have a transceiver and a latch, a separate one for the terminal. It's not the same ones used for the switches and for the LEDs. So Z80 would be hooked up to the data pins. So the data pins we hooked up to one side of these devices, the latch or the transceiver. And the other side will be hooked up to one of these. So which is which? Well, the receive for the terminal is actually hooked up to the sending on the Z80 side and vice versa. So you would hook up from the latch, you would hook that output of the latch to the RX, and the transceiver would be hooked up to the TX. And once you do that, everything will work. Now, getting back to the code. Okay, a few things I would like to mention. So this code is on GitHub, and it is under srfinc0/Z80. I provided this an ASM file, the assembly listing, a command file, and a binary file. And also, we'd like to mention the structure of this thing is just a main line at the top, a very simple program. Starting at the top, you can see we displayed a title on the display, and then we clear the lights, right? And then we start processing. So anyway. Let's see, I want to show you one thing in particular which puzzled me when I did this. Let's see if I can find it. There it is. The halt instruction. When I'm finished and the user enters a upper or lowercase x, I will halt the Z80, but the halt doesn't really halt the machine. I thought it did, but when I ran this at a low rate, a low clock speed of 7 hertz initially, then I changed to 15 hertz, and I looked at the M1 pin, which the LED was hooked up to, and that light was still blinking, even though I issued a halt. It didn't stop blinking. Well, that's because, as I found out later, the halt is actually causing the Z80 to execute no-op instructions without end. So you can halt that way, or you can do what a lot of people do I've seen, is just jump to itself, and that just loads the program counter with the beginning of that instruction over and over again. So it doesn't really matter. They both do the same thing in the end. So that is the end of this segment. I will show you how I burn this code onto the ROM in the next segment. And then the segment that follows, I will then try to show some things that I found out as I did this that might help you, caveats and tips and so forth. Anyway, stay tuned to the next segment. In this segment, Software Part 2, I will show you how to get your code onto the ROM chip. If you didn't use an assembler, you could skip the first 2 steps. You may have just coded this thing in machine language. Okay, assuming you use an assembler and you have one, I got mine from the internet. It was called Z80ASM. On the command line, I typed in Z80ASM, the file name I'm using, iostar1200.asm, and I will hit the enter key. Return. Hopefully. There it is. Assembled in less than a second. No errors. Okay. Now, next thing to do, issue direct command directory. And there's quite a few files here already in that directory. But I will locate the one we are interested in. We're interested in iostar1200.cmd, the output of the assembler. It is the command file. It also provides the listing LSD extension. Okay, so now we have that. The next thing to do would be to load a hex editor program. I'm using HXD. I will load, open recent files. It's probably in that list. It is the command file. There it is. Now, if you examine it, if you look at the top, there is some heading information, and we don't need that. So, how to find where the actual program starts, you would come to the listing, and you would see after the equates that the first line of code actually starts with 210201. And you find it here in the hex editor, 210201, so that we know we need to get rid of everything before it. Done. Now, the beginning looks okay. Now we have to check the end. What's this 02020000? We don't need that either, because I know that the program ends with character return line feed, 0D0A, so I will get rid of that. Done. Now, there is one more problem, at least in my case. The assembler I used apparently has some kind of bug in it where it introduced some garbage. And if I go to the end of the listing, and the reason I know that is because when I executed this program, I didn't get the behavior I expected. So the cursor bounced around and it started writing text over text. It didn't give me what I expected at all. So if you go up, I put a bookmark there. This line, which is the line right before the text, the Venerable Z80 demo, right? I see an ED51 Charlie 9 generated. And I can see in the listing, I can find that. I can look for it. You can see that first I find the string, the Venerable. And then I find these 4 bytes. There's 51 Charlie 9, and here is the ED. What are these bytes? They don't belong there. So I get rid of them. And that seems to do the trick. I have no idea why the assembler is doing that. So now I'm going to save as. There we go. And I'm going to rename this file. I'm just going to change the extension. It was command. I'm going to change it to binary There we go, bin. I'm going to save it. Yes, overwrite. Now we're good to go. So now we're ready to burn this code onto the ROM. Now, when I started this project, I was using these ROM chips. An M27 Charlie 512. So 512 bits being 64K, I'm only using 32K of it actually, but that's okay. You can see the window on these chips. These chips require ultraviolet light to erase them. So therefore, I went to eBay, got this unit here. It's very inexpensive. You just load this tray below with the chip, and you turn on the on-off switch, and you just turn the dial as far as you need, depending on how long you want to try to erase the chip. And in practice, it took me about 10-15 minutes, and the chip was erased. Well, I got tired of doing that after so many times, and I said, well, why don't I use one of these chips instead? Here we go. This is an SST 39SF020A. Now this chip is an EEPROM, and this chip, conversely, is an EEPROM. This is electrically erasable, this is not. So we can skip the step of erasing it with the light, ultraviolet light, and we could go right to the unit I used to do the burning. I secured an TL866 Universal Programmer. There's the box. There is the unit. Also inexpensive. So all you do is you take the chip, there you go, you find the notch, go to the unit, and first you really need to make sure that the pins aren't bent. That actually happened to me once. It will fail if the pins are bent. It will also fail if you have the reverse orientation. So I'm going to put that in, and I'm going to push the lever down. That looks fine. You can see there's a red light on now. That's the power light. When it actually reads and writes, the other light will go on. Now, yeah, what does it say on there? Run? Okay, so now we would go to the program that's associated with that unit. And let's see if I can find that. Okay, there it is, Mini Pro Programmer. There it is. It's Mini Pro version 6.85 in this case. Start off with all high values in every byte. Now, what we need to do, we need to load, and there is no recent menu item here, so I'm going to open, and I have to choose the file. Should be near the top. Let's see, there it is. We want the file I just created, not the command file, but the corrected bin file, the code with just the binary code. Okay, say open. The load mode is normal, file format is binary, and code memory is where we're going to. That's the region. We click the OK button. Okay, it's opened. It appears in the window, and you can recognize the 210201. And if you scroll to the bottom, well, let's see. You can scroll. You can see the code, the text, Venerable Z80 demo. Okay, so in order to burn it, all you have to do is click the program button. And that is the chip I'm using. Of course, if you use a different chip, you need to select it with the drop down here, which I've already done. And it remembers it from the next time, so I didn't have to do it again. Code memory is what you're using. And once you do that, it's just clicking the reprogram button, and there it goes. It erased the chip in 0.4 of a second. Pretty quick. A lot quicker than using the EEPROM. Now, it's actually transferring the code now. It takes just under 20 seconds to do that. Another few seconds, it'll be done. There it is, 19,438 milliseconds. Just in between 19 and 20 seconds. It verifies it for you, and it's done. The verification step took a little over 3 seconds. Now, I used to verify it manually before I trusted this unit, but since I've used it about 100, 200 times and it's worked in every case, the only time it failed is if I had a pin bent on the chip, or the orientation was reversed and the notch was at the bottom, or I failed to change the select IC dropdown. Other than that, it always worked, but in case you want to see it for yourself, you can manually verify it easily by coming to the fill button, and you would use high values and you would click OK. And there's high values displayed, and then you reread it in with the R button, and you just click read, and it's pretty quick. It's faster than writing, and it's a little over 3 seconds, and it reads finished. And if you move this out of the way, let's see, code is back. Except I wasn't at the top. There's the top. Okay, that's all there is to it. It's very simple. Now, there's one more thing I'd like to mention about the code. I'll bring that back up because this is the software section. I'm going to go to the top, go down a little bit. Okay. In the first machine I built, when I read a switch from the dip switch section, when I read a switch, I'm only using one of the 8 right in this case for this machine at the moment. And there's the instruction. Register A, switch port, which is the value 0. I compared, as you can see, I'm comparing register A to 0. That's not the way I originally coded it. I actually compared the value to 1, and I reversed the condition. So instead of not 0, I use 0. That's the way I thought it should work. But turns out it never worked that way until someday, a few weeks later, I was thinking about it, and I thought, kind of like out of the box thinking, why don't I just flip this around? So I did, and it works every time. The only thing I can think of is that the high and low values are not exactly 1 volt and 0 volts. It's actually, it might be close to 5 near the Z80. I think I saw 4.8 most of the time. But near the switch and near the I/O decoding circuit, sometimes I saw something like 3.3, 3.5. And in fact, when I checked some data sheets for some of these chips, the high value is actually, could be that low. So I'm thinking that since 0, the low, is very close to 0, it's more likely to accept this way. It just goes to show you that coding at this level, this is really nuts and bolts level, could be a little tricky. And that's about it. Now, in the next section, I will offer some helpful tips and possibly some caveats. By the way, did you know that in Britain, Great Britain, they actually pronounce the Z80 Z80? I thought that was kind of funny. Anyway, stay tuned. In this segment on Helpful Hints, I will begin with telling you why I got into this project in the first place. I found this book, Rodney Zach's Programming the Z80 lying around. I realized I never programmed machine language for the Z80 chip. I decided to do it, to try it. So then I secured this Radio Shack machine, which I bought from eBay. It's a Tris 80 Model 4 microcomputer. After getting the assembler, I created this disk editor program, which allows the user to read and write sectors on diskette files. But before I was able to get a working machine to do that, I discovered this RC 2014 kit I bought from Tindy Company in England, and it works fine, but it only allows the user to program in BASIC, and that wasn't my goal. So therefore, I waited a while until this one came out. They made an RC 2014 Pro. As you can see with all these boards in this package, I had many attempts and they all failed. It's a bit more complicated than the other unit. So I decided at that point, instead of keep trying to build that, to get it to work, I decided to try to build my own computer. And the first one is right here. It's the same as the one I showed you in the demo. except there is no terminal attached. All it has is dip switches and it has LEDs. Now let's work on this part. I will show you now a few helpful hints. Here is a regular standard breadboard. When I first bought them, I bought real cheap ones, bought like 10 at a shot, and had trouble getting the wires in and out of the holes. So I decided to get the better ones. The best one I had yet bought was from Radio Shack. But in order to make a computer, you need 4 of them, at least the one I built. So I hooked them together, and it was a bit flimsy. So I decided to get one unit already connected from this Make Ronix company, and that worked out fine. The holes in this board are pretty good. And the first thing you have to do when you use such a board is you have to connect the rails. The green wires are connecting the ground rails, and the red wires on the right side are connecting the power rails. And once you do that, power and ground is accessible to anywhere on the board. Now, hint number 1, when you connect the ROM chip on the board, you need to leave room between the wires on top of the chip and the chip itself so you can remove the chip easily. To do that, this is what I used, this flat screwdriver, small screwdriver, and I just placed it in the groove on one side, and I kind of used a motion of seesaw motion up and down, and on the other side of the chip I used another screwdriver right here, and between the two of them I was able to gently nudge the chip out of the holes and take it out without damaging the pins on the chip and without disconnecting any of the wires. Now, when I started the project, I thought it would be easier to just buy a kit of jumper wires, and here's one such kit. Unfortunately, there are 3 disadvantages with using these wires. One of them is that the lengths are fixed, the colors are fixed, and they could be brittle. I've had several occasions where on the board itself, the wires snapped and left the pins in the hole. Once that happens, it's very difficult to get the pins out of the hole, and you can't use that hole anymore. Okay, so now, once you decide to make your own using a wire stripping tool and needle nose pliers to bend the pins on each side, if you practice, you can make quite a few of them very quickly, as I have done. So I made quite a few. You can see the red ones, the blue ones. Now, regarding the wires themselves, if you use the same wires like this and the wires are bunched together like that, it's very difficult to see what connects to what. So I would advise using different wire colors, which I've done in another machine, and alternating them so you can see what connects to what. Okay, looking at the bypass capacitor. I made a diagram earlier. I didn't think it was very clear, so I want to clarify that. You can see the 0.1 microfarad capacitor. It's just a regular capacitor, no polarity. So then you can see the leftmost pin is connected to the topmost pin on the chip, and the other side is connected to the power rail. The rightmost pin is not connected to any pin on any IC, and it is hooked up with a yellow wire to the ground. I trust this is pretty clear. Many people have said that the capacitor has to be located as close to the chip as possible, but didn't show any diagrams, so I thought I'd provide that. Going to the oscillator, you can see I used a trimmer instead of 2 resistors. It's very convenient because the 3 pins sticking outside connect to 3 consecutive holes in the breadboard. It also provides a screw, small screw, and if you use that screw, you can affect the duty cycle, which I had set at 50% high, 50% low. In between the electrolytic capacitor and the trimmer, we have the 555 timer. I used a 2.2 microfarad electrolytic capacitor here to generate the clock frequency of about 7 hertz. In the other computer I built, I used a 4.7 microfarad electrolytic capacitor, and I was able to run at 15 hertz. This computer does not have a full can metal oscillator, but you can use, instead of a full can, you could use these quartz crystal resonators. Now, if you use that, you have to make your own circuit. Here's such a circuit. You can see 7.3728 is the same frequency as the one used by the RC 2014 kit. The only difference here is that these have 2 pins, and the full metal can, which is not on this computer, has 4 pins. So the 4 pins are used as, let's see how they use. The 1 pin is not connected, 1 pin is power, 1 is ground, and 1 is a signal. Okay, I used a slide switch for the reset circuit, because since the Z80 requires about 3 clock periods to reset, and a clock period is the same as a T-state, in case you're interested and didn't know that, by using a slide switch, you don't have to keep your hand on the switch, as with a tactile momentary switch. You could just slide it, move your hand away, wait, and when you're ready, just slide it back, and then the Z80 will start executing instructions. Okay, you can also see I hooked up the LEDs, a few of them, to Z80 pins. I have here 2 LEDs. One of them is the I request, the other is the mem request. This is the read, and this is the M1. So if you run it at slow hertz, like this one, the machine does, at about 7 hertz, you can see the lights blink on and off. You can tell what the machine is doing at any given time. Okay. I used 330 ohm resistors for the LEDs. And I did provide a parts listing on another screen in this video. That about does it, wraps it up. All comments and questions are welcome. I hope you enjoyed this video and have fun building your computer. So long.